Welcome all again to the first of our apps webinars for SC25 student cluster competition and IndySCC. I'd like to introduce, I guess in order that they appear on the author list here, Sema Abdullah, Xinglei Kao, and Zubair Khaled, who are our app experts helping us in this one. This one's we're referring to it as the Exascale Climate Emulator. Guys, take it away.
Thank you so much, Steve. Hello, everyone. My name is Samah Abdullah. I'm working as a senior research scientist at KAUST in Saudi Arabia. We actually have three parts of this presentation. I will present the first part. The second part will be by Zubair. He is working as an associate professor at Lahore University of Management Science in Pakistan. And our third colleague, Chun Lee, is working as an assistant professor at St. Louis University. So we expected, but it's not mandatory, but we expected that all of you have already read our paper and maybe have some insights about the work that we did last year. But if not, also we will cover this during this webinar. So the title of our paper was Boosting Earth System Model Outputs and Saving Petabytes in Their Storage Using Exascale Climate Emulator. As you can see, this work is actually a collaboration between different people from different places in the world, US, Pakistan, Saudi Arabia. And also they have diversity in their expertise starting from HPC, then statistics, and also earth science. So we have a diversity of expertise that helps to have this work done. So this is the team, including actually the SC committee during the award, the award that we got, the Gordon Bell Award. This is during SC24 last year, and we hope that one of the teams that attends here to also be on stage winning the competition at SC25 this year too. So the first part, I will talk briefly on what's the meaning of Earth system models and what's the challenges behind the computational and the storage needs for those models and the motivation of our work, and also about the main contribution that we have. Then Zubair will go with explaining the climate emulators and the phases that we have that you guys will go through during your use of our code.
Okay.
And at the end,
Lisa, okay.
Yeah. And Shanley at the end will go with the HPC innovations and explaining the meaning of runtime system and show some performance result of our work. So actually, to understand what's going on in the Earth related to the climate system, most of the existing work is relying on Earth system models. It's a kind of BDEs and physics running on supercomputers to simulate what's going on the Earth based on some historical data. And we are using this for actually understanding the data and also to do some kind of forecasting related to climate weather variables like temperature, humidity, and other variables. Those ASMs play a fundamental roles for what they called IPCC, and this is a panel that actually trying to forecast what's going on the Earth and the upcoming years, and also helps to understand the Earth more better so that we can take the actions. So those models actually is the main thing to understand the climate system. However, we have several models or even many models that can be used to simulate the data, the historical data that we have. And because of this, there is some work also or a project called SEMP6 project, which actually care about collecting the data coming from different models from different research group worldwide and trying to put it as one place for collecting all these data that can be used later by other institutes to maybe simulate more data or emulate those data. So for example, the last SEMP6 project actually collected around 28 petabytes of data using 45 models coming from different institutes. The problem is to store this data. Actually, those models generating data, and you are taking this data and you need to store them. And this is very hard to be stored, and it's increased year by year because of generating new data from those models. The other problem that you cannot generate data on site. So you cannot just delete the data and when you need it, you can generate it because generating the data takes time on supercomputers. Okay. And because of that, there is a main problem of how to solve this thing, how we can use the model and at the same time not keeping all these data and store it. And this is when climate emulators come. So the climate emulators is a kind of stochastic models designed to mimic the ESM behavior. So instead of keeping the data coming from the ESMs, you can just keep small amount of data and then use these emulators to emulate data looks like the data that come from this ESM. So in this case, you will not need to store the data anymore, but just use the emulator to generate the data as you want. Those emulator can quickly generate multiple emulation of the output of the ESM, and it's also can emulate data coming from different models, not just one model by one model. So because of that, there is recently progress on actually scale the climate emulators and make them generating more data and also higher resolution than existing. However, if we come to the literature of the climate emulator, until our work, the higher spatial resolution coming from a climate emulator cannot go more than 100 kilometer. Okay, and the future is telling us that no, we need more finer resolution than this because the data that will come later because of the increased improvement on different devices and other things that can capture those data and also from the ESMs show that we will need finer resolution than this. This is the main motivation behind our work is to actually build a climate emulator that can go to generate global data using historical data, very finer resolution in spatial and also in time, as we will see. So this picture has been generated by Zubair, actually. This can summarize the contribution of our work here. You can see in green all, so you can see on the left here, the work until 100 kilometer spatial resolution on the y-axis and the computational complexity on the x-axis. You can see easily that all the existing work here, you can see on those boxes, cannot go more than 100 kilometer resolution. On our work, we reached to 3.125 kilometer resolution. You can see how we scaled our climate emulator to actually cover a finer resolution compared to other works. And you can see the extension that we are doing here. When you see the dashed line, this is if we use an approximation to our method or to the climate emulator or to use exact emulator. For the exact emulator, you can see that we reach to this point and we can go far if we apply approximation. But for this work, we are doing exact emulation for the data that we have. So what's the contribution that we have? Actually, we developed and validated the first climate emulator built actually also by a set of authors from our group on another paper. We scale this by a factor of 245kx in total, 28x in space and around 8,000 in time. Actually, for the first time, we did this implementation using SHT, but depend on the work that's come from Jan and Zubair and Johnson on their paper in JASA. We built our emulator using 54.5 million spatial location across the whole world, and also we reached to high spatial resolution around 3.5 kilometer on hourly data, and we also train our model using 477 billion data points. We can see from what we did here that those ESMs dataset no more need to store them anywhere, which actually exceed petabytes, and you can find a lot of details about the storage need on this JASA paper and how we can remove all these data and just depend on our emulator to emulate the data for you when needed. All of this is part of our contribution from the science part. From the HPC part, also we did our all the scalability on different system and in different places in the world, starting from NVIDIA, from Summit supercomputer, that include NVIDIA V100 GPU. This system was on Oak Ridge. Actually, they have now Frontier replaced Summit, but at that time we used Summit. We also did some runs on Leonardo in Italy using A100 GPUs, also on Alps, the Grace Hopper based system and Switzerland, and Frontier on Oak Ridge with AMD GPUs. You can see here, this is the flops that we obtained from those systems to train our emulator. And you can see easily that we used 4 different types of GPUs, starting from V100, A100, NVIDIA V100, NVIDIA A100, the Grace Hopper Superchip, and also the MI250X AMD GPU. And we obtain at the end all these numbers. Very important, because also we will ask you to produce numbers the same as the number that we have. Not actually the same, but I mean you will use the same metrics to get us the performance that we are looking for from the hardware that you have, and also to show the scalability, strong scaling and weak scalability based again on the capacity of the hardware that you have. So this is the data that also you will use part of it on your runs. We depend on ERA 5 temperature dataset, 2 meter temperature dataset, and we used it up to 25 kilometer spatial resolution with a total number of spatial location around 1 million. We also train our model using hourly and daily data. 318 billion hourly data and 31 billion daily data, and we were able to scale our runs to 3.5 resolution. So the next, or part 2, will be presented by my colleague Zubair, and I will let him share the slides from his side. Thank you.
Thank you, Samay, for setting up the context and giving a very comprehensive overview of the work we did. Let me quickly share my screen. Yeah. So I assume my screen is visible. Okay.
Looking good.
Thank you, Steve. Yeah, so I will present the design of this Exascale Climate Emulator. In fact, to be precise, I will present how did we process these billions of observations in our pipeline to generate climate emulations and design the Exascale Climate Emulator. So this is the big picture we have. On left top, we have this climate data going as an input, and then we process it as we move from top left to the bottom left. And in the bottom left, we have climate emulations being generated. So moving forward, I will zoom into different blocks of this big picture, and I will explain the processing we did from climate data till climate emulation. Yeah, so in the first step, let me quickly explain this climate data. So this climate data is defined on a spherical manifold. It is defined on a surface of a sphere. It's a 2 meter surface temperature data. It could be any climate variable. But what we considered is that is defined over n theta number of latitudes times n phi number of longitudes and t number of time steps. In our case, n theta was 720, n phi was what 1440, and t depends on the number of years we take. So we took hourly observations. We also took daily observations. So we did both of them. So in the first step, once we get this data, so this data is defined over 3 dimensions. In the first step, we remove the mean trend. The mean trend is something that is varying over time for each spatial location. And we model the mean trend as this mean trend part, MT, plus some variance that is kept in bias is sigma, and then ZT is the stochastic part, right? R is the number of realizations. Since we only have one realization, we'll keep R is equal to 1. And this, in the first step, we estimate or we model this mean trend MT. MT is defined by some DC component beta 0, and then some lag component beta 1, and then we have these periodic components as well, right? So once we learn the mean trend that corresponds to learning parameters B0, B1, B2, these AKs and BKs, right? And this sigma. So once we learn the mean trend by simple using regression, so you will be given the code of this as part of the first task. So once we know the mean trend, we subtract the mean trend from the data and we divide by the standard deviation. And what we get eventually is the stochastic component. So for each spatial location, we learn sigma, these parameters that define the mean trend, right? So once we have these parameters, we subtract MT and divide by sigma, we obtain the stochastic component, right? So this is the stage one, right? Once we have the stochastic component, so the next step is we transform this data using spherical harmonic transform to obtain the spectral domain representation of the data, right? So stochastic component ZT, again, this is defined over space and time. For each of time point, we take the data on the sphere, we compute its SHT, and we obtain this spectral domain or spherical harmonic domain representation of the data. So after this step, so what we have for each time step, we have the spectral domain representation of the data. So once we have spherical harmonic domain, so we vectorize this 2D representation into a single vector. And when we do this for each step, we obtain capital T numbers of uh, spectral domain representation of the data, right? And the next step is for each uh, time step, sorry, for each spatial location or for each bandwidth, we model the temporal variations by simple autoregressive process. And FT is the input, and we remove this autoregressive part, and what we obtain in the temporal D mean component psi t. So using this, we simply compute the Gram matrix, and that results into the covariance matrix. We estimate the covariance matrix using this equation. And what we get eventually is a matrix of size L squared by L squared. If you're using the 25 kilometer resolution data, the size of this matrix would be roughly 0.5 million by 0.5 million. And the advantage we get by using this spherical harmonic transform is what we get eventually, the covariance matrix that represents the anisotropies as well in the data. There has been work previously, as Sammy mentioned, in which people assume that we can assume the process to be azimuthally symmetric or the process to be isotropic. But in this work, we do not take any assumption. We consider that the data has an isotropies, and we capture those anisotropies in the covariance matrix. So once we have the covariance matrix, so the next step is the most computation intensive step, and that would be perhaps quantifying the overall performance of your pipeline. That is the Cholesky decomposition of this covariance matrix. And in this Cholesky factorization, we use the tile-based Cholesky and mixed precision. Very shortly, Shinle will explain more details about this. But we are using this tile-based Cholesky and mixed precision techniques to carry out Cholesky factorization efficiently. So once we have Cholesky factorization, it means we have this matrix V. And if we know V, we can simply use V to generate the climate data, right? So covariance matrix was capturing all the anisotropies and statistics of the data. Once we know the decomposition of U as V, we can use it to generate more climate data. So from V, we can do the reverse process. We first obtain this IT, and then autoregressive part, we simply add that to obtain the spectral domain representation of the data. We do, we do inverse Laplace harmonic transform for each time point to obtain the stochastic component of the emulation. And once we have the stochastic component, we add the mean trend using these parameters which we obtained at the time of removing mean trend. And once mean trend is added, that variation in the space is added, what we obtain is the final YT, which is a climate emulation that is statistically consistent with the actual data because it has the same covariance matrix what we had for the climate data. Here, this is just an illustration that was developed by KAUST visualization team. So I will first show the simulation, and then we will also show the emulation. When we presented this in the conference, we had these 3D glasses as well, so you could really see the 3D. But here we don't have 3D, but we can. Yeah, the simulation and. And then we have this emulation as well, which is, as I mentioned earlier, they are statistically consistent, and we have demonstrated this in the paper. Yeah, okay. Yeah, I think I stop here, and I will hand over now to Shinle, who will explain the HPC innovations we did in the work. Over to you, Shinle.
Okay, thank you, Sam and Zubai for the review and the science part. So I will give some presentation about the HPC innovations. Could you see my screen? Is it good?
Yes, Shinle.
Looking good.
I can see.
Okay. So then, in the HPC world, actually, it's not that easy. So on the lower side, so we have different kind of the hardware is different provided by different vendors. We have the more many core CPU system, we have heterogeneous GPU system, and on the top side is also we have very different kind of applications, right? So if the application want to efficiently map to the hardware part, so there is a huge gap. So then what we need actually is abstractions between the application part and how the application can efficiently use the different kind of the window the libraries and also the hardwares. So one of the most important abstraction will be the program model. So like I think you already familiar with the high level language like the C, C++ pattern, right? So I think you use already. So in the HPC part, so because we need to do parallelize the code running on the many core heterogeneous system in the program paradigm, because the evolution about the AP hardware is also evolving. It can be from the I think back to uh, 2 decades or 3 decades. That is the BSP models and early massive passing. The reason for that is before I think before 2003 or 2004. So there are no many core systems. So you can do one. There will be one core on one chip. So then in that part, so you can just use the MPIs. And later on, because the many core systems, so that is the hybrid mode called the MPI plus X, like the MPI plus pthread, MPI plus OpenP. So you use the MPI for the communication, and then for the local computation, you use the pthread or OpenP. And later on, because the heterogeneous architectures, so the model also evolved from the MPR plus S to and also to the MPR plus RY. Where you can think about is the GPU programming, like the CUDA. So for NVIDIA GPUs or the AM GPUs use the heap. So this is the involving. So for all these three kind of model, you can think about, you can see there are some limitations. First, the user need to express to describe how the parallelism. First, describe your job, describe your algorithm, and then how to efficiently to map this algorithm onto hardware. You need to deal with everything, and also you need to deal with all the synchronizations. This is the first challenge. The second challenge will be, you can see from these three models, so there will be they also most likely the BSP model. So you will do first step, do some synchronizations, and then do the next step. So this is not quite efficient. So then later on, so I think back to 10 years ago, so the task-based runtime system become more and more popular, especially in the linear algebra and also the scientific computings. So in the task-based runtime system, the user will be to express the algorithm like here in this figure as the DAG, that is the directly cyclic graph. And you can see because provided by the fine-grained task, and then the synchronization in the previous model is removed, then you can have more better performance. This is the first advantage. The second advantage is that this is another abstract layer on top of the MPI, the CUDA. So then the user just need to provide this DAG. So the right figure shows the compression trace about the two traces of the same algorithm on top with the MPI, and then the bottom with the pass and runtime system I will describe later. So you can see clearly the trace will be condensed. They will be have the higher performance. So here, these slides I talk about what is PASEC. PASEC is a runtime system that is asynchronous, architecture-aware, and with fine-grained tasks can run on distributed medical heterogeneous architectures. It's an ecosystem actually, so it has its own communication engines built on top of different communication library like the MPI, like the GasNet. So, and then it also has its own device management. You can run your code on different architectures, many core CPU system, heterogeneous architectures, AMD, Intel, and NVIDIA. So it also has its own scheduling, data management, all of these things. So the user does not need to care about all these levels about runtime system. The user just need to be using the domestic language here, on the top part, domestic language to express your algorithm and describe your algorithm to the runtime system. In PASEC, there are three domestic languages I will detail later. So one called the DTD, that is dynamic task discovery. The second is the compared repetition called PDG, and another one called template is the C++. So the user need to be describe the algorithm to runtime system, use the DSLs, and the algorithm will form as here as the directly cyclic graph. You can think of it as a task graph. Why there task graph? Because you divide your work into more pieces. Because the more pieces, there will be some dependencies. Because first, you need, like here, you need to finish this task and then do the next one. The user will describe this algorithm to the runtime system, and the runtime system will do all the remainings per how to efficiently run on the different architectures. For the DSL, the first one, and this is the most easiest one, I call the DTD. Why is it the most easy one? Because it still follow the with rewriting the sequential algorithm. So this is example as in the linear algebra, the QR algorithm. So in the QR algorithm, there is this kind of for loops. So in the when the user write the algorithm, they still follow these for loops, the sequential code, but providing additional information how you partition the data and how you read or write on data. That the runtime systems will be dynamically create the DAG and then running on different architectures. So because this is doing on the runtime system, the runtime need to be construct the DAG and then to consume the DAG. And because the runtime system and all the process, all the nodes need to have this information. So this is sequential. So this one has some scalability issues up to, for instance, 1,000 nodes. That is a little large scales. And then because of this, so we have another language called the PDG. So this one follows the styles when you're writing the MPI code. In the MPI code, you need to have the explicit send or receive. And here, the same idea. For the task, one task, you may be like in the gym. You have three datas. The gym is the matrix multiplications. You have three data. You have the A, B, and the C. So you need to receive these three data. So like in the MPI, you need in the input arrow here. So you need to explicitly receive the data, and then you need to also explicitly send the data to your next task. So this part, because user need to explicitly describe the DAG, so you need some effort how to describe the DAG like you write in the MPI code. But the benefit is that this part will be happen at the compiler time. In the past, we have our own compiler. So with this is happen at the compiler time, because happen compiler time we will have a loss optimization. For instance, the collectives, that is an issue for the pre's for the insert DTD part. The another one is the called template the city template time graph that is between the PDG and DTD. So because we do not use in this project, so if you're interested, just look at the PASEC website. So the another on APC innovation is about mixed precision. So I think right now mixed precision is very hot. Why is that? I think we need to have better, faster time to solution, and therefore we have high performance, right? So in our algorithm, why we can use mixed precision? The reason because we have multiple blocks, and each block will be some block have smaller norm, and this is some performance for the three generations about the NVIDIA GPUs from the V100 to the A100 and to the H100. You can see that there is a huge performance gap from the down precision to the high precision. It's not like the CPU part, the down precision, the single precision, double the performance of the down precision, high precision, down precision, single precision. On the GPU, because the tensor cross, so the performance between down precision and single precision, there's a huge gap. And we're able to leverage this part. And there are already so many researches in the literature about this back to, I think, half a century. So that is the iterative refinement that right now is still widely used. So what we are using is different than the traditional method. We use the adaptive method. I will give you a little details in the next slides. And we use multiple precision, double, single, and half precisions. But we only keep a single matrix copy. And that is the requirement in the iterative environment. You not only keep the original matrix, you need to copy the reduced precision matrix. So this is our adaptive mixed precision algorithm look like. So this is, for instance, in the Cholesky, you partition the matrix in the fine-grained tiles, and then the precision we determine at the tile level. Each tile will have its own precisions. So the benefit for this one is that because you only lacking the attention, you only keep the most important informations. For instance, some tiles is very important, you just keep in the high precision. Some tiles is less than important, so we just use the low precision. In this case, we not only reduce the time to solution, but we also only keep one copy of the data. So we also reduce the memory requirement. So I do not give more detail about that. So when you have the code, if you want to see the details, so this is how the algorithm look like. So you can see because of this fine-grained dependency, fine-grained the precisions, so there'll be lots of challenge, the load balance, how to do the data movement efficiently, how to do the precision do. So then the runtime system, this is how the runtime system will support that. So this is two details. I just give you some ideas there. So for instance, in the distributed computing, the most important thing is how you place data, right? I want to do the computation on one node. Maybe the data is not local to me. How efficient do the data transfers? And the second thing is, for instance, in some algorithm, the collective is very important. How we efficiently support the collective operations. So all of these things the runtime system will support. And the goal is that the runtime system will be hide all the complexities from the users, only have the syntax of the very simple sequential code. So this is the purpose of the runtime system we're doing. So the next will be some our Exascale performance that we're running on 4 different clusters, as Sammy already showed at the beginning. So this is the first one. It will be on Leonardo up to 1,000 nodes. That is around 4,800 GPUs. And the next one, the Summit, around 3,000 nodes. Each node has 6 V100 GPUs. And then the next is on multiple nodes on the Alps. Alps is the grasshopper, so up to around 2K number nodes. And this is the largest one on the Frontier. Frontier is the AMD-based GPU systems, and each node will have 8 GPUs, logical GPUs. And this is the largest ones, almost runs on the full scale as the Frontier systems. Okay, to the summary. So this work design Exascale Climate Emulators, enabling the ultra-high spatial resolution emulations, and the data we trained is on more than 300 billion hourly and 30 billion daily datas. And for the HPC side, so the mixed precision, random systems, scalable on multiple systems, and performance. This is the performance on 4 different systems, or should be 4. Then the last will be some initial task. So the task 0 will be, so first read the papers, familiar the framework. You have any questions, you can I think we have our Slack channels. You can just drop a message there. And for the task 0, you have 3 subtasks. The first, download the data set. So this is the website. You can download this site. And the second, you just read the input, remove the means as by already said in the stage 1 in the presentation. And the third will be you need to learn a little bit what is the runtime system. This is quite different than the MPI code. You need to, because you want to get high performance on your hardware, you need to learn a little bit about the information. What is the task-based models, how it performs, and how to efficiently run the hardwares. So this is the link. There is a wiki page. So you do not need to know the details. So there are some slides for that. You just read that. And then the next task will be install the softwares, and we will give you some instruction later. So we do not have that many dependencies, but we need to have some dependencies like the Lepaki, all of these linear algebra libraries, and there will be more information will be coming. Okay, thank you for listening. If you're interested in the paper, so I think you can scan the QR code here. Okay, any questions?
Thanks, Xingle and Zubair and Samo for a really informative talk. So as well as the QR code here, if you go to the SC25 webpage, you should also see a link to the paper that you can click on directly. I'll pre-answer a couple of what I think are likely questions coming up. I know teams are very keen to get hold of the code and start downloading it and asking questions and trying things out. You have hopefully by now noticed in the final team composition section of the submissions, one of the things we've asked you for is GitHub handles. What we'll be doing is collecting up those GitHub handles and using them to provide you access with some repositories that will have the code and or the code for the different apps that we'll be using. When it comes to Q&A, also I'd like to remind you, please don't email the app experts directly. We'll have a issues section for each app. on those GitHub repositories, and we'll use that for Q&A. And that way, questions about the app and answers about the app are visible to everybody, so everybody can see the same information. I guess another question likely coming up, particularly on the Indy side, is access to Jetstream, and I think that is also coming up soon.
Oh, I see.
And Steve, the IndySCC teams, everyone in this stage, in the final team composition form, was asked to provide an email address that I can use to add them to the Google group. And so that will be the main way going forward for announcements. And then, of course, there's the GitHub to open issues with the two apps. So I'm not planning to do a Slack channel for the IndySCC, so it's the Google groups and the GitHub that are the main ways to communicate with app experts and benchmarks and the committee.
Cool. Thanks for that, Layla. So yeah, watch Google Groups for announcements, and we'll use GitHub issues for Q&A. All right. Thanks again to our presenters and to everybody for attending and being a part of the competition. And we'll see you all as things approach.